everybody. My name is Dennis Marschner. I'm a founder of Dema Software Solutions and I'm computer scientist in the field of artificial intelligence, deep learning, and robotics. Today in this talk, I want to present my master thesis, which is called Human Hand Motion Embodiment Mapping from RGB images to robotic hands. I will start with the introduction and motivation behind this topic, and afterwards I give first a short outline. The presentation will take in total 30 minutes. So have fun and let's begin. Robots become more and more powerful every year. As the fine motor skills of humanoid grippers increase, so does the number of potential applications where robots can assist humans. The necessary physical capabilities have already been demonstrated in an impressive way. Many robotic grippers already have more than 20 degrees of freedom. Of course, these grippers are less robust than those with few degrees of freedom. But apart from the robustness, there's another big issue. The crucial question is, how can we develop robust control algorithms for these complex robotic hands? It is clear that these gripper capabilities far exceed the limits of explicit programming. So what we need is an intuitive way to easily teach robots. One promising approach to bypassing explicit programming is called imitation learning, or learning by human demonstrations. Here a human teacher demonstrates hand motions and the robot imitates these motions. But the problem is that learning almost always takes place in laboratories. Typically, expensive and complicated hardware setup, such as a motion capture system, are needed. And often a lot of noisy data is generated and has to be post-processed. In other words, hand imitation learning involves complex training sessions with robotics experts only. The overall goal of the master thesis is to enable the teaching process of complex control algorithms with inexpensive hardware for non-robotic experts. The problem is reduced to the transformation of an RGB image to a robot gripper pose. The task is to extract the hand posture of the human demonstration and translate it to joint angles so that the robot imitates the human and shows an overall similar posture. In this presentation, I first give an overview of technologies in the field of 3D hand pose estimation and show the possibilities and limitations of monocular color image-based methods. Secondly, I present the 3D hand mesh model MANO. It is a promising hand state representation which could serve as an interface between different motion capture systems. Next, I present a complete software pipeline for extracting the robot angles from RGB images. The pipeline design is inspired by the work of Fabisch from 2022, which describes a modular approach to embodying hand motions from human demonstrations, with MANO serving as an intermediate hand state representation. I realized this pipeline by integrating different perception and actuation modules. The final implementation is integrated into a new self-developed Capture Studio. It's a complex GUI application to control and visualize live the pipeline process. Finally, I will show two experiments. First, the system was tested in imitating the American Sign Language. Secondly, I show results of various grasping experiments for which I included the dataset HU3D from Hampali et al. All right, so motion capture of human hands is a demanding task due to the dexterity of hands, high angular velocities, and many degrees of freedom. Non-optical methods use typically glove-worn sensors and involve complex calibrations. Different solutions were proposed, which use stretch sensors, inertial measurement units, electromagnetic trackers, or bend sensors. The problem is that they can generate noisy data or drift over time. Furthermore, person-specific hand shapes are rarely addressed or need complicated calibration methods. The other group of motion capture systems are optical methods. Here we have a large continuum which ranges from single markerless monocular color image-based estimators to commonly known marker-based motion capture systems. In between are markerless and marker-based solutions with color or depth sensors in a single or multi-view setup. Monocular color sensors are inexpensive and already available on most mobile devices. So they are useful in everyday situation, but have not the highest precision. Mocaps instead are expensive, have high precision, and are typically in a laboratory setup. Here we see a current state-of-the-art architecture to estimate 3D hand poses from RGB images published by Kulin et al. To generate ground truth training data, a large collection of YouTube videos were processed. First, I used a simple 2D hand pose estimator to detect key points in the image frames. Then followed an iterative fitting of a MANO hand mesh. The results are used as a mesh for a feed-forward network with a mesh convolutional decoder. In other words, it is an approach for end-to-end neural network training with mesh supervision that is obtained through an automated data collection method. Now some words to MANO. MANO is a differential 3D hand model whose surface mesh can be fully deformed and posed. M is a linear blend skinning function that is applied to a rigid hand body with shape TP, joint locations J, pose parameters θ, and blend weights W. Linear blend skinning is a skeleton-driven deformation technique and is typically used when animating bodies or virtual characters. The shape parameters describe person-specific deformations of the hand, and θ describe all possible joint rotations. Here we see two 3D hand pose estimation solutions. Minimal Hand is a lean solution for capturing hand motions from RGB image at over 100 frames per second. The second solution is called Media Pipe Hands. It's a powerful and easy to use hand and finger tracking solution, but cannot estimate a MANO hand mesh. And in this slide, we see a demonstration of HO3D. The authors created a dataset consisting of a MANO and object mesh during grasping scenarios. It shows quite well a 3D hand pose estimation solution where many estimators like Minimal Hand and Media Pipe Hands would have reached their limits because of the hand-object occlusion. Honotate works only so well because the system was trained via a multi-view approach with known objects. Now I summarize typical problems of RGB-based 3D hand pose estimators. First, it is problematic if the image has very low resolution and shows illumination effects. Second, there are many different human hand shapes and skin colors that have to be considered. The labeling of 3D hand poses is very expensive, so there is probably no million-scale ground truth dataset. And an important problem is hand object and self-occlusions. Physical interactions and grasping tasks are generally challenging, but still the estimates seems good enough for imitation tasks. Social sign language and hand gestures show good estimation results. They are probably very suitable for imitation tasks. Now I will present the first part of this software pipeline, the perception part. This is about reading the hand pose from a simple RGB image and describing it as a MANO hand state representation. I combined and integrated two different perception systems. The first pipeline, S1, is based on Minimal Hand's keypoint and MANO mesh modules. The second pipeline, S2, combines the keypoint estimator of Media Pipe Hands with the MANO mesh estimator of Minimal Hand. So both pipelines have an RGB image as input and estimate a MANO hand state representation. The pipelines were qualitative tested live in front of a webcam. The differences are particularly clear if for the demonstrated hand poses pinky, index close, and index spread, as can be seen in the last three columns. S2 achieved better results than S1. The reason is that the 3D keypoint estimation from Media Pipe Hands provides more accurate estimates for complicated finger positions. Now we can see a small demonstration that I recorded myself, which also has the same background and lighting conditions. I have set the wrist rotation to 0 because in this way we can better see the finger estimation, so it is more stable. Now comes the second step of the pipeline, the actuation part. Here's a task to convert the MANO hand state model into robot gripper specific joint angles. But first, some words about the target system. The shadow dexterous hand is a humanoid, human-inspired, multi-fingered robotic hand, and its tendons can be motor-driven controlled. In total, the system has 24 degrees of freedom, which is very suitable for many complex gripper control algorithms. And now I want to introduce the following state-of-the-art method proposed by Lee et al. In 2020. It's called vision-based teleoperation of shadow dexterous hand using end-to-end neural network. The method translates depth images into joint angles of the shadow dexterous hand. The TeachNet was trained with 400,000 synthetically produced pairwise training data. But here lies also the limitation. The question is how to generate such synthetic data pairs automatically. Therefore, first 3D joint locations of the human hand were mapped to the robot hand shape. To do this, the authors proposed a static joint position and joint direction mapping function. This also includes the transformation from the human to the robot base frame, which was positioned at 2 small green triangles near the wrist. The second step is to run an inverse kinematic module in the gazebo robot simulation environment. Here, finger collisions are also taken into account by imposing a penalty on joints that are too close to each other. The human skeleton is very flexible and only the robot gripper has a rigid body. Furthermore, similarity between the human hand and the robot hand cannot be defined clearly. The proposed mapping function is static and only derived from the human and robot default resting pose. This function is probably the bottleneck, and also it doesn't support different mapping goals. Furthermore, person-specific hand shapes are not addressed. I want to propose a new approach which considers person and goal-specific embodiment mapping for different robot gripper types. In the case of my master thesis, the goal is topological similarity. Topological similarity or pose mapping means not only mapping the fingertips, but the whole posture or function of a pose. The goal of the actuation pipeline is to map a person-specific MANO hand state into the joint angles of different robotic grippers. If we focus only on the internal kinematic skeletons, we can clearly see the different kinematic structures that need to be addressed. Since the transformation to the robot shape is the crucial step, the hand embodiment mapping function could be described as a function with the input parameters J MANO, beta, and RT, where beta is the person-specific shape. So the function returns the joint locations of the robotic hand RT in its own frame. The number of joints I depends on the number of controllable joints of the robotic hand. But first, we have to meet some conditions. The kinematic structures of both hands need to be aligned and coupled. This means the robot can't have more than 5 kinematic chains, and we have to define which joint is coupled with which joint of the MANO. A minimal robot hand could, for example, have only 1 kinematic chain with 2 joints. We can describe the embodiment mapping with parameters like joint offsets, pose offsets, and joint scales. It is important that these values are assigned according to the kinematic chains. This means, for example, that if we rotate joint 14 by a pose offset, as shown in the middle, this changes the position of the child joint 15, but also of all following joints, such as joint 20. The next parameter is the person-specific shape beta. Here we see 2 examples of how beta values deform MANO more to the robot shape. The same robot hand in different poses can lead to completely different shape values. In total, the mapping configuration consists of 6 parameters. The transformation T MANO robot describes an initial transformation between both skeletons. Also, we need a skeleton scale value that is applied to all joints simultaneously. The goal is to minimize the distance between all coupled joints in 3D space. Furthermore, for each kinematic chain, the individual joint offsets, pose offsets, and joint scales have to be calculated joint by joint by minimizing the individual distance between coupled joints. Now we see the summary of the proposed new MANO embodiment mapping function. The method allows generating different hand configurations over different ground truth similarity pairs. These configurations can compute target-specific desired 3D key points in the robot gripper shape of a given robot gripper. These key points can then be transformed into gripper angles using inverse kinematics and further post-processing steps such as collision detection. This flexible approach can prospectively optimize the limited generation process of synthetic training data for a TeachNet, as in the method of Lee et al. Next, we look more closely at the different hand embodiment configurations that arise with the algorithm when we use different manually created ground truth training data pairs. Here we see such 8 manually created training data pairs for which different configurations were derived. For these topological similarity pairs, I try to include as many different poses as possible. And here we see in the 4 rows 4 different configurations for the data pairs point, fist, piece, and OK. The first 4 columns show the ground truth meshes and corresponding joint skeletons. The 5th column shows the calculated beta value. The 6th column visualizes at which point the joint offsets had a stronger influence. And the last column visualizes which part of the hand were more deformed by pose offsets. We can clearly observe that the configuration values differ across all poses. That is interesting because all examples are calculated from the same MANO and robot mesh, which not differ in their kinematic structures, but only in the poses. This figure shows the calculated scale value of the entire skeleton for each of the 4 similarity pairs, point, fist, piece, and OK. Now we also introduce the results for the hand embodiment average configuration, which can be seen at the right side. This value describes the average scale value of all generated hand embodiment configurations. It can be observed that all configurations scale the MANO skeleton about 20% larger, except for the fist pair. And this anomaly becomes noticeable also in the next illustration. Here we do not see the scale values of the entire skeleton, but those of all individual joint bones, each as an average value per finger. The hand embodiment configuration of the fist pair has the largest scale values here. For the fist pair, it seems that the scaling towards the robotic hand was not achieved via the skeleton scale, but via the individual joint scales. Furthermore, it can be observed that the pinky finger seems to be scaled most strongly in all pairs. This can be explained by the fact that the pinky finger of the shadow hand is significantly longer than the pinky finger of the MANO hand. Now I show a small demonstration of the actuation pipeline. In the left example, only inverse kinematics was used to directly map the fingertips. The right example uses the same fingertip mapping, but first the average hand embodiment configuration was applied. To put it all in a nutshell, my final implementation of the perception and actuation pipeline consists of an offline and an offline component. The offline component learns hand embodiment configuration, which can be applied online to a MANO hand state representation to get desired key points in a robot frame. For the creation of all manually created annotated similarity pairs, I developed the Capture Studio, which is the main user interface of all online components. This software architecture was finally used in the evaluation experiments. Now I present the results of these 2 experiments. The first experiment was about the imitation of American Sign Language. It was conducted with the ASL dataset published by Pujold et al. 2011. It consists of 24 letters demonstrated by 5 different adult subjects in front of an RGB camera. In total, there are about 12,000 images consisting of 100 images per letter and subject. I picked randomly 1 image per letter for every 5 subjects. First, I want to show some results of the hand key point estimations. In total, only 8 from 120 estimations failed completely, and 4 showed minor misestimations. Sometimes it is hard to judge for humans, as for example in the case of letters M and M. But here in this slide, we see mostly successes. Now I show the mentioned failures in the first row. And as we can see, the key points are completely misestimations. So this I declared as complete failures. The second row illustrates the slightly light misestimations. In the case of letter K, we can observe that the thumb tip is not detected properly. And in the case of letter A, R, the index and middle finger key points are not crossed, but they should. And the letter P, we can see the thumb and index estimations are slightly slipped. In the last row, we see the next pipeline step, the key point to MANO estimations. A common problem that occurred is that the sum of the MANO mesh is not properly posed. Now we see all pipeline step results from the input image to the final robot pose. These two examples show quite well how success and failure can be very close to each other. Unfortunately, the pipeline at the moment cannot judge that the estimates was wrong, so this error carries over the subsequent pipeline steps. In the second row, the MANO mesh shows a right-handed hand trying to follow a pose that belongs to the left hand. The MANO hand has no constraints that prevent this unnatural pose. Compared to the first key point estimations, the estimation of MANO was less successful, but still good enough to recognize at least some letters. Apart from the sum problem, the MANO fist seems not to close tightly enough. The hand embodiment mapping module seems to have successfully established the topological similarity between MANO and the robot. However, the figure only demonstrates the last step of the pipeline, so all previous accumulated errors are not visible. This figure demonstrates the results of the entire pipeline. For each letter, there is the input image and the final estimated robot pose. Inaccuracies increase significantly throughout the pipeline, making many letters hard to recognize or easy to confuse. Overall, MANO estimations seem to be the step in the pipeline that produced the greatest inaccuracies. The final letter imitation is not sufficient to teach the robot all American Sign Language poses. For the last experiment, I used more accurate MANO estimates. The dataset HO3D includes various MANO hand mesh estimates while grasping different objects. The authors of HO3D developed algorithms that correct the automatically collected hand and object meshes in a multi-view approach. In total, the dataset consists of 77,000 images from 68 sequences of hand-object interaction taken by 10 people with different hand shapes. Yellow marked pixels of the MANO hand indicate that this vertex has a maximum distance of 4 mm to the object. Red pixels mean that the MANO hand has intersected the object. The first experiment shows MANO holding a sugar box. After applying the actuation pipeline, we see that the robot hand seems to be well positioned, but the middle and index fingers clearly intersect the object. This grasping attempt would most likely have failed in real test. At this point, no dynamics or physical constraints were taken into account. The second grasping experiment also shows the sugar box, but with the different finger configuration. As far as can be judged from these plots, the grasping imitation seems to be useful since no significant defects can be seen. But again, no dynamics and physical constraints are taken into account here. The third experiment shows MANO holding a mustard bottle. It shows the problem which occurs when the robot fingers are longer than the human fingers. The robot hand is not closed far enough, so the mustard bottle would probably fall down because there's not enough friction. But nevertheless, this pose seems to be a conceivable initial pose to initiate a grasping manipulation process. The last experiment I want to show is MANO holding a mark. Unfortunately, the pinky finger clearly intersects with the object. Probably this error could have been avoided if the mapping goal was concentrated on matching the fingertips. But we can also observe that the MANO mesh already intersects with the object. However, I think basically the robot mapped pose looks very useful. So let's make a final conclusion. I will now summarize which aspects I talked about and what my contributions were. First, I summarized the challenges and technologies in the field of human hand motion capture with a focus on monocular color image-based methods. Physical interaction and grasping tasks are demanding, but in principle possible. For sign language and hand gestures, the hand pose estimation results are even more accurate, which opens up many areas of application. At this point, some words to the previously mentioned publication from Alexander Fabisch. It is called a modular approach to the embodiment of hand motions from human demonstrations. Here, a professional motion capture system is used to estimate the MANO hand, and the hand demonstrations are then transferred to humanoid robotic hands of varying complexity. My contribution as a co-author was the subsection motion capture of human hands. My second contribution was a proposal for a MANO embodiment mapping approach. This is a person and goal-specific approach which is suitable for different robot gripper types. This approach could prospectively use to generate a synthetic large-scale training data set of similarity pairs. Furthermore, I developed a complex GUI application to quickly run tests with different data sets or a RGB webcam. And the last contributions were two qualitative experiments, one with the American Sign Language and one with a more advanced MANO object mesh estimation. I hope that my presentation provided you insights into the challenging task of mapping human hand motions from RGB images to humanoid robotic grippers with different kinematic structures. And now some final words to the outlook. In general, I think the most promising steps in the actuation part are integrating the time dimension and physics. So forces, dynamics, torques, and physical plausibility are important factors. Although we should consider to optimize trajectories over time in a reinforcement learning environment, for example. The last promising aspect for me would be integrating tactile sensors in grasping tasks. But at the end, the overall approach has to be tested on real robots, since there is still a lot of invisible error sources to solve. At this point, I would like to express my interest in working on a publication that evaluates the learning of gripper control algorithms via simple RGB images on a real robot system in an even more professional way. So please let us keep in touch, and together I'm sure we can reach very interesting new insights for the community. And with this, I thank you very much for your attention. And of course, I am pleased and looking forward to every questions and feedback you might have. So please contact me if you're interested in this topic. And yeah, then have a nice day.